In this class, we're going to learn the technique known as integration by substitution. So we're going to learn many techniques for finding antiderivatives this semester. The most widely used of all of these techniques is the one we cover today. It's the one that if you can't immediately do it, this is the first thing you should try. In the same way that the chain rule allowed us to differentiate many new functions last semester, the substitution method will allow us to anti-differentiate many new functions this semester. So spend time in the coming weeks reviewing the material from this lesson. Okay, so I'm going to do the process for U substitution on this integral. Don't worry about frantically writing down what all the steps are. The step-by-step process is on a reference sheet near the beginning of the packet if you need to refer to it. Okay, so I want to take the integral of x times the quantity x squared minus 1 cubed using a U substitution method. I could expand this all out. I could cube x squared plus 1, multiply x squared plus 1 times x squared plus 1 times x squared plus 1, do all that multiplication and combining like terms, and then distribute an x. But it's just way too much algebra. We're going to do U substitution. So the way we have to choose a U, a function within the integrand to be our U. So the way you choose U is it's typically an inside function. It's typically the inside of a composition. And it's a function whose derivative also appears in the integrand. Okay, so my choice for U in this case is going to be x squared plus 1. Okay, so the reason I chose it is because it's inside a composition. It's the inside of something cubed. It's some stuff cubed. I chose the stuff, the inside. And the derivative of U is 2x, and there's an x that shows up in the integrand as well. So it differs by a coefficient, but that's okay. So the derivative of x squared plus 1 is 2x, and I have an x to the first also in my integrand. So once I've chosen U, I calculate du dx. Calculate du dx, the derivative of x squared plus 1 is 2x. Then you pretend du dx is a fraction, and you solve for the dx. So I would multiply both sides by dx, so I get du equals 2x dx, and then try to get the dx by itself, so divide both sides by 2x. So we get dx equals du over 2x. Then we make some substitutions. Okay, so I go back to my original integral, which is x times x squared plus 1 cubed dx. Okay, everywhere I see the expression that I called u, I'm going to replace it with a u. And I'm also going to replace the dx with du over 2x. So this becomes the integral of x times u cubed times, instead of dx, I'm going to write in du over 2x. So this magical thing happens where my x's cancel. Okay, so now I have an x on top and an x on the bottom, and they cancel. So this becomes the integral of 1/2 u cubed du, because that 2 is in the denominator of a fraction, so it's a 1/2, and then I have u cubed du. Now I can take the antiderivative of u cubed, so I have 1/2. The antiderivative of u cubed is u to the 4th over 4 plus c. Now that I've taken the antiderivative, just replace the u with what I had let u equal at the beginning, x squared plus 1. So this is going to be 1/8. I'm multiplying 1/2 times 1/4 times u to the 4th, which is x squared plus 1 to the 4th plus c. So just to summarize, the steps were choose a u, strategically choose a u. It's often the inside of a function, the inside of a composition, and its derivative may be off by a coefficient, but its derivative also shows up in the integrand. So we chose x squared plus 1. Then you calculate du dx and solve for dx. Then you go back to your integral and you start substituting in u's and du's. Yes. So yeah, we plug in our u's and du's. All your x's should cancel at this point. If they don't, you've chosen a bad u, or u substitution just isn't going to work. Integrate in terms of u and then substitute back in. Okay, so we're going to have a brief look at the u substitution step-by-step walkthrough at the beginning of the packet. We won't go through all the steps together, but I want you to see the reference sheet. There we go, page 7. So choose a u. It might take several guesses, but you have some guidelines, right? It's typically inside of a composition, and its derivative also shows up. So for this example, the integral of x squared times 3 plus 4x cubed to the 5th, we would choose u to be 3 plus 4x cubed because it's inside of a composition, and its derivative involves an x squared, and I have an x squared also in my integrand. So once you choose u, find du dx, solve for dx, substitute everything in, cancel, 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 simplify, 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 and then what's left should only be u's. Integrate with respect to u, replace u with the stuff, and you're done. And then some hints for choosing u are down here. And you can study this in depth like as you go through your homework, but I just wanted you to see that it was there. Okay, so one tip-off that you should try u substitution is if a function and its derivative, possibly missing a constant multiple, both appear in the integrand. But there are no hard and fast rules as to when a u substitution will work. Sometimes there's some trial and error involved in the choice of u. This is normal and it's expected. You won't always choose u correctly the first time. Sometimes you can't see ahead of time what choice of u will work. So the technique doesn't always yield a tractable integral. You can end up, if you end up with both u's and x's in the integral after you have substituted, then the u you tried probably won't work. So there's a typo in this problem. I want this to be the integral of 3x times cosine of x cubed. Throw a cubed on that x. Okay, so the choice for u, the natural choice for u, is the inside of the cosine function, right? This is a composition. Typically, we choose the inside of the composition to be our u. So du dx would be 3x squared, which means that dx is du over 3x squared. And now we substitute everything in. So I've got the integral of 3x times the cosine of u times dx, which is du over 3x squared. And then what happens is my 3's cancel, and one of my x's cancels, and my final integral is 1 over x times the cosine of u du. This is not helpful. All my x's didn't go away. So this is just not a u substitution problem. So it didn't work because the x cubed, its derivative did not show up in the integrand. Only 3x was there. If that had been a 3x squared, we would have been golden. When this happens, what you chose for u may just be a bad choice, but it may be that u substitution won't work. Okay, so here's how we evaluate a definite integral. If you have bounds on the integral, when you're using u substitution, Start by calculating the indefinite integral. Find the antiderivative first. So you use substitution, get the indefinite integral. This is what we just did in the first problem of the demo. So if I want to calculate the integral from 0 to 2 of x times x squared plus 1 cubed dx, I now know the antiderivative, so I just write it down, x squared plus 1 to the 4th over 8, and I evaluate from 0 to 2. So it takes a little work to get the antiderivative, but once you have it, you just plug in the bounds like normal. So if I plug in a 2, I get 2 squared is 4, plus 1 is 5. 5 to the 4th is 625. Can somebody confirm that for me? And when I plug in a 0, I get 1/8. Five to the 4th, 625. Okay, good. So 624 over 8. Can you reduce that for me, somebody? 78. Great. Okay, so note, writing the integral from 0 to 2 of 1/2 u cubed du will surely lose you some points on a quiz or a test. What's wrong with writing that? Yeah. So 0 and 2 are x values. Remember, a definite integral is saying find the area under this curve between x equals 0 and x equals 2. When I changed variables to u's, I left these bounds as x's. Okay, so what you're going to do is do your work separately to find the antiderivative and then plug in the x values. So this is just kind of just bad notation. You've got x values on the bounds, but u's in the integrand. All right, you're going to get started on your activities. Call me over if you're stuck.